Well, welcome everybody. Thank you for coming out to Grand Rounds this morning. We're very fortunate today to have Colleen McNamara from University of Virginia as our speaker. Colleen gave a really exciting talk on her laboratory-based investigations yesterday at South Lake Union, and today she's going to bring us up to date on more clinically related topic of immune cell modulation for cardiovascular disease prevention. So sort of in the post-lipid era, lipid-lowering era, what can we do to decrease cardiovascular disease further? So Colleen is from Ohio. She got her bachelor's degree at Ohio State and attended the Medical College of Ohio in Toledo. She's spent the rest of her professional career at the University of Virginia, where she has risen to the rank of full professor and is a professor both in the Department of Medicine and in the Department of Molecular Physiology and Biological Physics. She holds the Francis Myers Ball Endowed Professor of Medicine title there at the University of Virginia, and her research work is focused on the role of B lymphocytes in atherosclerosis, diabetes-associated vascular disease, as well as perivascular adipose tissue and atherosclerosis. Her professional honors include serving on the editorial board of ATVB, serving on the board of scientific counselors for the National Heart, Lung, and Blood Institute intramural program, and being a charter member of the Vascular Cell and Molecular Biology Study Section at the NIH. I was particularly impressed in reviewing her CV by her training record, despite the fact that Colleen doesn't have a PhD. She has trained many graduate students and mentored them to get their PhDs, and they've been quite productive while they worked in her laboratory. She also has current funding from the NIH as a principal investigator, both as on an R01 award and on a long-standing program project grant. She is a project leader. So Colleen is going to bring us up to date on immune cell modulation in cardiovascular disease. Thank you very much.
Okay, so Sam told me you'll be able to hear me if I put this on. I got it for you. So is that correct? Can everybody hear me okay? Yeah? Okay, great. Well, good morning, and thanks for coming. I know it's quite early, and appreciate everybody being here. And really appreciate David's kind introduction, as well as the wonderful invitation to come here. And I had a great time yesterday catching up with old friends. I've known David in April for 25 years, and many others, Mike Rosenfeld and others. And so it was great meeting new people yesterday, as well as connecting with some old friends. So David reminded me the thing to share, because I suspect there are fellows in the room, and I had actually never stepped foot in a research laboratory until my cardiology fellowship. So I'm what they call a late bloomer in the literature. You too? Yeah, David too. So at any rate, I had, when my colleagues between first and second year of med school actually were going into research laboratories for the summer, they said, oh, you should do that. You can, make this money, get exposed to research. I'm like, why would I do that? I'm going to be cathing people, but as it turns out, just goes to show, you just keep your eyes open, and, you never know, and just follow where kind of your heart takes you. So it was really during the course of my residency that I began to really warm up to, or really wanting to know more about the mechanisms of the diseases that we were treating, because while we were doing great stuff, there was still a lot of disease burden. And I think a lot of that stems from the fact that we don't fully understand many of these processes. So that does segue to some degree into what I'm going to talk about today, because what I'm going to talk about today is what people call residual risk, kind of meaning the risk for cardiovascular disease after we've done everything that we have, which is a lot, but there still actually is quite a bit of residual risk in terms of heart disease risk. So, and I'm going to be talking about immune cell modulation. Nothing to disclose. And this is the outline of kind of what I'm going to talk about. I'm going to talk a bit about the evidence for inflammation, for the inflammation hypothesis in atherosclerosis, and then talk about the studies that are testing that inflammation hypothesis. So the idea is, you know, we've got these great lipid-lowering drugs, and we're really doing great things with that, all of which is true, but we still have a pretty high residual risk, and the thought is the next approach may be modifying inflammation. So there's been 2 trials, and I'm going to talk about those. One is the CANTOS trial, which was just released last year at the European Society of Cardiology meeting. Paul Ricker is the PI, and he presented the data. It was published in September in the New England Journal, if anybody wants to read the original report. And then their follow-on paper, and I don't know if they're just going to release these in little stages, but a follow-on refinement of looking at the data from the CANTOS trial was just published 2 weeks ago, or it was January 27th in the Lancet. So these are sort of it's a hot off the press clinical trial looking at regulating inflammation in people who are maximally treated with statins, and their LDL cholesterol is well treated. And this trial was supported largely through Novartis. So it's a pharmaceutical trial, 10,000 people, $800 million, and I'll show you what we got for that, or what they got for that money. There's another trial ongoing at the NIH, and it's called CIRT, and I'm going to touch on that a little bit as well, although it's not finished enrollment, and it won't finish enrollment until December of 2019. So I won't talk in great detail because we don't know the results yet on that trial, but I'll tell you a little bit about it, and then we can kind of think about sort of pros and cons and how either one or both of these may be fitting into your armamentarium in terms of approaching your high-risk patients going forward. And then lastly, you know, I want to talk about some of the work that we're doing in my laboratory to get more specific targeting of immune cells that may be involved in cardiovascular disease. And in particular, we're interested in really bolstering endogenous anti-inflammatory mechanisms. And particularly, the work we're doing in my lab is those anti-inflammatory mechanisms that'll target OXLDL, as we feel like that's one of the big initiators of inflammation in the artery wall. Okay, so this is a diagram from this review from Nature Immunology by Goran Hansen, and it really sort of depicts decades of murine, as well as some humans work, but largely animal work, I should say, that has really allowed us to get a greater understanding about the role of the immune system in atherosclerosis, and what immune cells are actually players, how things start. So I'm just going to go through it a little bit. The data supports that we know, again, LDL is linked to cardiovascular disease. LDL gets into the wall in a concentration-dependent manner. The higher it is, the more that gets into the wall. But LDL itself isn't particularly pro-inflammatory, doesn't really avidly get taken up by these by macrophages to create foam cells. But once it gets oxidized by enzymes from the endothelial cells, it does become an antigen, and it becomes really very pro-inflammatory. And it stimulates the endothelium to express these adhesion molecules, which then capture the immune cells, and they're coming into the wall because the artery wall is saying, I've got a foreign invader. So they're coming in really to clean it up. But it's this really, the more oxidized LDL you have in there, the more of these immune cells that come in. In some ways, they just establish and start this cascade of inflammation. They come in to really get rid of the LDL, but in the interim, they're releasing cytokines and chemokines, which sort of further fuel the process. And ultimately, many immune cells have been shown in, again, both animal and human studies to be in these plaques, even mast cells, neutrophils, macrophages, T cells, foam cells that have engulfed the lipid. And even as David said, we're very interested in perivascular adipose tissue in the adventitia. There's even organized immune networks on the outside of vessels in the area where there are plaques that are felt to be regulating it as well. And those are composed of T cells, B cells, dendritic cells, and there's antigen presenting cells as well. So in the end, I'll let you know that in the end I'm going to be talking to you about the B cell, as David said, which is an immune cell we've actually come to get quite interested in. But hopefully this will convince you that the immune system is a big part of atherosclerosis. And right now, other than the anti-inflammatory class of statins, we don't have specific anti-inflammatory weapons in our armamentarium. There we go. So that's sort of showing you, at the pathophysiologic level. But then, what do we really know about patients? And again, we know from a variety of human studies, actually, that it's both LDL and cholesterol and inflammation that really are important for risk. And you can see here the probability of event-free survival. If you have a low LDL but a high HSCRP, your risk is about the same, is actually very similar to if you have high LDL cholesterol. So inflammation is an important risk. And some of additional evidence is that the plasma levels of inflammatory biomarkers, including HSCRP, robustly predict first and recurrent CV events, independent of lipid levels. You have to have a fast old thumb. I'm going back and forth between buttons, so bear with me. Statins are both lipid lowering, as we know, and anti-inflammatory, and the greatest benefit to statin therapy accrue to those who both lower LDL cholesterol and HSCRP. And Jupiter demonstrated statin benefits in those with low LDL cholesterol but elevated HSCRP. So there's a lot of clinical evidence that inflammation is very important as a risk factor. And then I'm this is a meta-analysis studying the use of methotrexate it wasn't studying the use of methotrexate for CVD. It was looking at studies that use methotrexate, low-dose methotrexate, for rheumatologic diseases. But what's interesting is one of the most striking endpoints in these studies of rheumatologic diseases is that there's less cardiovascular disease. And so again, additional evidence that modulating inflammation can lower cardiovascular disease, but I also choose this particular set of evidence because methotrexate is the drug that's being used in the CIRT trial. And it's based, largely on this set of data that, again, when we weren't asking the question about cardiovascular disease, we found that it was reducing cardiovascular endpoints. So that trial is now proactively asking that question. So this is the paradigm, if you will, is that there are we have individuals that are high risk, high LDLs, high HSCRP, and they really should get high intensity statin therapy as much as you can give them. After that, we end up finding that people have some residual risk. I mean, there will be some people that are high risk that still have elevated LDLs, and then the answer is to think about ways to further reduce their LDL cholesterol, calling them residual cholesterol risk. But there's individuals who you've got their LDL to goal, and yet their HSCRP is still quite elevated, and these are the residual inflammatory risk patients. And so really the idea is they need to be targeted with additional inflammatory reduction, and to date there is not a specific therapy that is approved specifically for inflammatory risk reduction, although once I show you, we'll go through the CANTOS data, and I think they're moving forward with taking that to the FDA, and likely it or in some variation form will be available in the next year or two for use. So how common is this residual inflammatory risk? Okay, so this is just looking at some subjects from a couple clinical trials, prove it and improve it. And you can see here is the key down here. These are the individuals from those trials that had residual inflammatory risk, meaning their LDL was less than 70. But their hs-CRP was still over 2, so they were inflamed. These are the people with residual cholesterol risk, people with both, and then people with neither, so those that were really kind of well treated. But you can see there's quite a bit of residual inflammatory risk, and you know, the residual inflammatory risk is in this group as well as in this group. I mean, they have this group has both. So, it's a large proportion of our patients. So these are the two trials, and like I said, CANTOS has been published, and we're going to spend more time on that this morning. CIRT is testing the inflammatory hypothesis by evaluating whether or not low-dose methotrexate will reduce rates of myocardial infarction, stroke, and cardiovascular death among stable coronary artery disease patients with type 2 diabetes or metabolic syndrome, because those conditions are associated with enhanced pro-inflammatory responses. And like I said, their plan is to get 7,000 patients. They're a little bit more than halfway there, and they're gonna enroll. There's about 360 centers enrolling. A lot of these are private practice physicians that are enrolling these subjects as well. So I don't think we'll hear anything till 2020, because they're not going to stop enrolling until the end of 2019. So why CANTOS studied Canakinumab? So why study Canakinumab? And so it's with the hypothesis that IL-1 beta, which is a pro-inflammatory cytokine, is responsible for or mediating much of this inflammation that leads to enhanced cardiovascular risk. And in part because IL-1 beta, which is produced from the inflammasome in response to injurious stimuli like cholesterol, neutrophil extracellular traps, atheroprone flow or hypoxia, or whatever your patient's risk is or injury is, activates the inflammasome, which makes IL-1 beta. IL-1 beta also stimulates IL-6 production, which is also an inflammatory cytokine, and both of them lead to elevated CRP. So it was known that blocking IL-1 beta was going to be able to bring the CRP down, and I showed you all that evidence that CRP is really very much linked to risk. So that's why this particular pathway was chosen for the first test of the inflammatory hypothesis. In addition, there were animal studies to suggest that blocking IL-1 beta would be atheroprotective as well, but you know, so it supported it, but I think more importantly it was its known effect on CRP. So Canakinumab is a high affinity monoclonal antibody, so it's one of these biologicals targeting IL-1 beta. It binds and functionally neutralizes its bioactivity, so there are IL-1 receptors, so it blocks it from being able to activate the receptor. It has a very long half-life, about 4 to 8 weeks, with CRP and IL-6 reductions for up to 3 months. And these are some of the biological effects of inhibiting IL-1 beta, again, that makes it appealing as potentially an anti-inflammatory for cardiovascular disease. It acts on the endothelium to reduce leukocyte adhesion. It's reducing endothelial procoagulant activity and inflammatory mediators. There are receptors, again, so the blockade will act to reduce proliferation and inflammatory production by smooth muscle cells, as well as leukocytes. And blocking it will block IL-6, which will end up reducing CRP production as well. I just want to draw your attention because if we get time to talk about it, if anybody has any questions, it'll be quite notable when you see the results. I'll just draw your attention that it also has an impact in cancer and stem cells, and so it inhibits this epithelial to mesenchymal transition, which is implicated in oncogenesis, and also can reduce metastasis. So this was the design of the CANTOS trial. And again, taking stable coronary patients. They were originally planning on taking 17,000. But as the study was moving forward, disappointingly, the event rate was so high that they didn't need 17,000. So about 20-25% of people on high-dose statins are having their second infarct. So at any rate, so they dropped the number to 10,000 because they could see that that was all that they needed. So they're stable coronary patients on statins, angiotensin blockade, beta blockers, aspirin, and it's a population that has a persistently elevated hsCRP. So it's that residual inflammatory risk population that I told you about. So they were randomized to placebo and then 3 different doses of Canakinumab, 50, 150, and 300, and it's given sub-Q every 3 months. So just like many of these biologicals. The primary endpoints were non-fatal MI, non-fatal stroke, and cardiovascular death. Secondary endpoints, total mortality, new onset diabetes, and other vascular events, and then there were some exploratory endpoints. So here are the results. This is from the September New England Journal article. And it shows that indeed, as expected, Canakinumab significantly reduces CRP levels at all doses, but obviously in a dose-dependent manner. And it happens early, so it happens in the first 3 months. This is with the first dose. It comes down and then stays steady throughout the trial. Doesn't do anything to LDL or lipid values. So it's really kind of an ideal drug, and this is why they selected it as well, is because they really want to test this hypothesis that modulating inflammation makes a difference. So you don't want to be changing the lipids as well, because then you can't sort out which is which. So no effect on lipids whatsoever from Canakinumab. And this is the initial results, is that there was a 15% reduction in the primary endpoint. There was this 39% reduction in hsCRP, as I showed you, no change in LDL, but 15% fewer infarcts. And here's where I'll show you, here's the cumulative incidence of the primary endpoint, which was predominantly infarction. And you can see in this population, they're kissing close to 25% event rate between 20-25. And so again, this is really a high risk population, and they could reduce that by 15%. So it's statistically significant, but it's not that clinically or biologically overwhelming, right? So I think people looked at this with a little bit of mixed emotions, because the other thing that I would tell you is, like all biologicals, it's like $16,000 a dose, right? So you know, it's going to be a pretty expensive therapy for getting this 15% reduction. And look at the patients, there's still a lot of residual risk. There's still 20% of your patients even after that. So you know, it's nice because it confirms the inflammatory hypothesis. If you modulate the immune system without changing lipids, you can you know, afford this reduction. But we, you know, as clinicians, need to scratch our head and kind of, you know, with the cost of healthcare and things like that, kind of think about this a little bit more. So let me give you some more data. If you actually divide the patients out by CRP, by these, if they're on treatment, if they're less than, if you can get them to less than median, or if they were kind of greater than the median. And you can see that the further down you can get the CRP, actually now we're getting, right, a 27% reduction. So a more significant reduction. So if, you know, so that's may allow us to be able to identify people who would have the greatest benefit, that we would consider this kind of expensive therapy for. So that was intriguing. Then the other thing I want to tell you about is additional outcomes of being treated with canakinumab. And the one that's, I think, for me, the most remarkable is fatal infections actually went up. So not entirely surprising. So you're broadly inhibiting the immune system. So there was a significant increase in fatal infections. And likely related to the fact that there was a significant increase in leukopenia. And interestingly, as I pointed out to you mechanistically how IL-1 beta can act on other systems, there actually is a significant decrease in fatal malignancies. And so this was not expected from the trial. And most of this was actually lung cancer malignancies, although that wasn't the only malignancy. So I think this is really intriguing, and I think that we're going to see a lot of trials now in cancer subjects using IL-1 beta blockade based on this cardiovascular trial. The other thing not surprising that was changed was there a reduction in all forms of arthritis, because again, as an anti-inflammatory, so that really isn't surprising. And you know, one of the things is there really was a lot of consistency of hazard ratio across all these cardiovascular endpoints, but I think what's most notable about this table is down here in the right corner. So this is CV death and all-cause mortality, no benefit. Okay, so, and likely it's related, or certainly the all-cause mortality loss of benefit, even though you're having fewer infarcts, is because of this increased rate of fatal infection. You know, why it was not significantly different in terms of cardiovascular events is they weren't all, you know, certainly weren't all fatal infarctions, and it was just a 15% reduction. So again, the hypothesis is correct that if you modulate inflammation, you'll give less heart attacks, but we're still kind of left a little bit wondering what to do with this clinically. Again, does it make sense to jump on the bandwagon? So for reasons that I'm not really sure of, it seemed then had a second publication just a few weeks ago, January 27th, 2018, that came out in Lancet with a little bit more information about looking at subsets within this trial. And looking at, I figured I'd do that at some point in time, different tertiles of CRP, and yeah, and you can see that actually with the people with the lowest CRP actually did have quite a good a 29% reduction now. So it really does seem to sort of parse out by CRP. The data I was showing you before about the 15% reduction, no change in all-cause mortality, all that stuff was all comers into the trial. Okay, so everybody that came into the trial, which was some people who'd had infarcts but had stable coronary disease, lipids, you know, treated, but elevated hsCRP, if you give it to all of those people, then you don't get any all-cause mortality. But again, you know, we get a better reduction in major adverse cardiac events if in the group that you get the best reduction in CRP. The other thing I find really kind of notable about this slide, which I think is really interesting, is if you look down here into the groups, this is the top tertile, middle tertile, and lowest tertile of CRP, and these are people that are treated, you know, with the effective dose of canakinumab, and you can see that you have responders, you have non-responders, right? And you have people who intermittently respond. So it's not like everybody got a CRP reduction with the canakinumab. Okay, so it's not. It's kind of looks like, you know, equal proportions of people are responding. So, which is similar to many of our trials, unfortunately, and why there's such a role for personalized or precision medicine, because when we do these trials, we may have a p-value, you know, like we certainly do here, but not everybody's responding, and yet many of these drugs have really important side effects. So I think there's a real interest in trying to identify beyond hsCRP what some other biomarkers might be that could predict response to some of these expensive and potentially hazardous treatments. But at any rate, so this was really quite intriguing. It looked like, if you really look at the people that got their CRP down, we really, let's look a little bit more at those people. And when you divide it by those on Canakinumab treatment whose CRP is still elevated, again, no significant benefit in CV death or all-cause mortality. But if you look at those that you got the CRP down, now we have reduction in CV death and all-cause mortality. So there will be a subset within these patients that have residual inflammatory risk that we may be able to identify to help us decide on risk. And my understanding, the NHLBI is partnered with Novartis in terms of some aspects of this trial, and I talked to the program officer and about this, and he told me that the plan, Novartis's plan, as when this drug gets approved, is to give the first dose free. Okay, so you saw from that graph, first dose, the CRP comes down after first dose. It's down at 3 months. So if you're less than 2, then you and your doctor might want to think about spending, $16,000 a dose to prevent your second heart attack if you're very high risk, right? And at least you know that you're likely to get a CV death benefit and an all-cause mortality benefit, and you didn't, they gave the first dose free. So that's the current strategy for which this compound will be moving forward. So in conclusion, from this part of the discussion is that placebo event rates really approach 25% at 5 years in people in this high-risk subgroup of people whose lipids are well treated, supporting a significant residual risk in statin-treated post-MI patients. And that treating residual inflammatory risk does reduce recurrent MI. Canakinumab does increase risk for infection, and there was no difference in the total population in all-cause mortality. So it would be important to develop biomarker strategies to figure out who will get that benefit. And again, the magnitude of HS-CRP reduction following a single dose identifies those most likely to benefit, and in this subgroup, CV and all-cause mortality were significantly reduced. Yet, as I pointed out when we looked at actually the numbers down there at the bottom of the graph, Canakinumab actually failed to reduce HS-CRP less than 2, and actually a large number of subjects. So, we still have that residual risk in those individuals. And we're actually involved with collaborating with a group from Virginia Commonwealth University who are using IL-1 receptor blockade for the treatment of heart failure, actually, to look to see if we can identify at a immune cell level what some of the mechanisms might be for why people don't respond to IL-1 beta blockade, and perhaps develop then a strategy for these individuals, again, that are yet very high risk but aren't even responding to Canakinumab. So, as I said, we need to await the CIRT results. It's projected to end enrollment December of 2019. Methotrexate is significantly cheaper. As you know, that's been around for a long time than biologicals, and it's already approved for treatment of rheumatoid arthritis. It's in general better tolerated, but it's not like it's side effect free, right? So people will have a lot of GI side effects. So it may be that we'll need to be looking at something else in that. But if they get similar benefits, and again, methotrexate inhibits IL-6 and brings down CRP levels as well. So if we get similar benefits, this may actually be what we would be looking to in the future, just because of cost and sort of lower risk, although not risk-free. But our interest in my laboratory actually is in trying to think about therapies that could maybe specifically target cardiovascular inflammation without targeting the inflammation that you need to fight infections, and as a way of getting perhaps even more effective inhibition of inflammation, and yet not having bad side effects. So in order to do that, we really need a better understanding of the cardiovascular specific or selective immune mechanisms involved in atherosclerosis. So back to our diagram here, and as I told you, many immune cells are involved. In my laboratory, we've been focusing on B cells. And hopefully I'll convince you that that's actually a good thing to focus on. And I'm going to show you a little bit of data. But I have to first introduce you. I don't know, like you, I told you the story that I'd never stepped foot in a research lab until my cardiology fellowship. And so, you know, as a late bloomer, though, it was really exciting. So when I went into this research lab, I still wasn't really sure that I was going to do that, you know, because I really liked the being clinically active. And I was really pleasant, I didn't know if I could do it. You know, it's another whole nother way of thinking and acting, and so, but when I did step into it, I really just loved it, and it turned out it worked out very well for me. And actually, it was around that time actually that I originally even met David through him coming and being an external advisor for one of these grants that we were putting in. That I was helping the attending that I was working with put in. So again, always keep your eyes open. And so why am I saying this again now as I put up this B cell schema? And that is, I finished my fellowship, got my KO8, and was studying the role of vascular cells, so vascular smooth muscle cells, which is very intuitive that they're involved in atherosclerosis. So I got an MD PhD student that came to train into my laboratory, and we were studying a gene that, you know, was regulating smooth muscle cell growth in the response to injury, and we said, well, let's see, you know, what it does to atherosclerosis. So we knocked it out in an atherogenic model, and lo and behold, there was a marked increase in atherosclerosis. So this gene is ID3. I won't talk about it any further, but and it was in both ApoE knockout models, LDL receptor knockout models, whether you fed them a Western diet or didn't feed them a Western diet. We saw the differences at 4 weeks, 8 weeks, 32. So clearly this thing was really atheroprotective, so we were really excited about it. This wasn't a global knockout, though, and so it's knocked out in all cells. And it's like, how are we going to figure out how it's doing this? We got to figure out what the important cell type is. So as many people do, we did bone marrow transplantation in the mouse, which allowed us to see if it was a marrow-derived cell or a non-marrow-derived cell. It turned out to be marrow-derived, and so we were really then, that was as close as we had gotten, and so then we learned a technique where we could digest the whole aorta and do flow cytometry to allow us to quantitate what marrow-derived immune cells were in the aorta in the, you know, our knockout mouse and our wild-type mouse. And what screamed back at us was, which was different, was B cells. I was B cells, but I'm a cardiologist. So it was an existential moment for us, because the idea is, what do? Do you fearfully run back to your smooth muscle cells and say, I can't, you know, I don't know. But, you know, that's why it reminds me of the story of just getting into the lab and keeping your eyes open, and then you realize, oh, I do love this. So we just decided that we had to follow the science. So I've become an immunologist. Even so much so that people have actually talked to me about putting my hat in to be chair of this immunology department. I have to tell them I'm not an immunologist, I'm a cardiologist. So then they don't want me anymore. But at any rate, so we, I was not, and I actually, in all honesty, I was in vascular biology, and I'd never heard of B cells in atherosclerosis before. So I don't know how many of you all have, but probably you have, but I hadn't. So, but we just decided that we had to follow the data. So that's why I'm showing you B cell subsets now, because you probably have a better understanding of B cells than I did, but you may not understand that there are various subsets of B cells, so they're not all created equal. Some are actually atherogenic, have been shown through murine studies to really promote atherosclerosis, and those are largely, although all the answers aren't in, so this is sort of a largely thing. Those are largely B2 cells. And the B2 cells might be the one that you think about more often. That's the one that hangs out in your spleen, and when you get your flu vaccine, these antigen-presenting cells present that flu antigen to your follicular B cells. They get a little help from the T cells, and they then end up affinity maturing, isotype switching, and make very high affinity class-switched IgG antibodies that in most flu seasons would protect you. So those are the B cells that most people think about. These are bone marrow derived. But there's another subclass of B cells. And again, when we first had our data, we just knew B cells too. So, and everybody kept saying, what subset? And we were like, B cells. So but as it turns out, there's another subset called B1 cells. And these cells are actually really fascinating. They're fetally derived. They are highest when you're born. So we have them. Animals have them. We have them. They're highest when you're born. They go down a little bit over time, but not substantially, but it definitely are highest when you're born. And they actually make predominantly IgM antibodies, and they do it without any T cell help and even without antigen presentation. So they're really a fascinating class of B cells. And so that's what I'm really going to be focusing on. So these IgM antibodies that they make are called natural antibodies because you're born with them and you did not get exposed to anything yet, and you have your highest titers when you're born. So they're thought to be germline encoded. And they actually recognize these moieties on LDL that are created when LDL gets oxidized. So they don't recognize LDL very well, but as soon as, and remember I showed you when it gets in the wall, it gets oxidized and becomes foreign. And that's what these IgMs recognize. And when they do that, they're actually able to block oxidized LDL uptake by macrophages, as well as block ox-LDL stimulation of endothelial cells to make inflammatory chemokines, cytokines, and sort of fuel this whole process. So if that just sounds like, well, yeah, maybe in mice, and that's a nice theory, I'll show you that one of my collaborators, I've been collaborating with Sam Tamikas, who many of you probably know, for maybe 15 years or so. And Sam is really the leader in the field of lipid biomarkers in cardiovascular disease. And in particular, now he's really doing a lot of work with lipoprotein(a), but in particular, a lot of these oxidatively modified LDL compounds. So this is just a figure from one of Sam's paper in the Journal of Lipid Research, but he has really multiple publications where he's looked at the association between IgM to different forms of, and here it's to a copper oxidized LDL. I'm coming over here because I've been talking about oxidized LDL, and you may wonder what MDA is. So MDA is malondialdehyde. So this is an aldehyde derivative that forms on LDL in response to oxidation. So all of these are oxidation end products on LDL when it gets oxidized. They've all been shown to be present in the wall in atherosclerosis. So Sam showed that as your IgM to any of these oxidatively modified LDLs go up, your risk of having significant coronary stenosis, in this study he used coronary angiography, goes down. So there's this inverse relationship, again, from this protective IgM antibody that I told you about. Again, it's blocking ox-LDL doing all these bad things. So that all fits. And probably, most recently, one of the studies Sam published is from the Bruneck-Hark study, which I really love the data in this. They had drawn blood on subjects 17 years ago. So they had that plasma, and then they were able to follow them. So not only did they have imaging evidence of coronary disease, but they had events, of course, which is really what we care about, right? And consistent with all the data that Sam has correlating it with imaged coronary disease, there was an inverse relationship between IgM to MDA LDL in cardiovascular events over the subsequent 17 years in this population. And it actually was able to, I know we all set that bar as well, but does it do anything better than the Framingham risk score, right? So in the paper they showed that if you put this into the model, you could actually get people reassigned to more accurate risk categories. So it actually does augment the Framingham risk score. And notably, there was not that association with the IgGs. Again, that's the antibody that's produced by those B2 cells, which are felt to be atherogenic, so that all fits. So I'm going to just quickly go through a scenario that summarizes probably 5 years of work, basic science work in my laboratory, but I think you'd rather see that than bars and graphs and plots. So this is how, again, these B1 cells are working. And like I said, LDL gets into the artery wall, getting oxidized by enzymes that are produced by the endothelial cells. And that oxidized LDL stimulates macrophages through toll-like receptors and other things to release inflammatory cytokines, but also the ox-LDL gets taken up through scavenger receptors and creates foam cells. When you have B1 cells making these IgMs, and I told you the IgMs have been found in the plaque, those IgMs then can block this process because they bind up the oxidized LDL, and so these pro-inflammatory pathways don't occur. And we've actually, through, like I said, many years of work, have identified that a chemokine receptor, so there's a receptor on the surface of these B1 cells that tells them where to go, is actually associated with how much IgM there is in mice. And so we think that this chemokine, or actually we've shown, it's unpublished data, but we're getting ready to submit it, that this chemokine receptor regulates these cells going to the bone marrow and spleen, which is where they make their antibody. And so if you don't have this chemokine receptor, your levels of those protective antibodies, if you're a mouse, are very, very low. And so this is sort of the murine work that we then moved into some human translation. So we have a protocol in our lab when people come into the catheterization lab. If they're willing, we ask them if we can get 100 mils of blood. And what we can do with that blood then is we can harvest the cells, and we can use a technique called flow cytometry, which allows you to put labeled antibodies on the surface of cells so you can identify them, and we can identify this chemokine receptor too. And we can quantitate within these human B1 cells, which these are just the markers that depict them, how much CXCR4 they have. Then we take the plasma and we send it to San Diego, to Sam Tamikis, and he measures these antibodies for us to MDA LDL. And what we found is that in people that have a high percentage of their cells are B1 cells, of total B cells are B1 cells, they do trend to have higher levels of IgM to MDA LDL. So that would make sense, the more of these B1 cells. But what's even more notable, sorry about that. What's even more notable is MFI is mean fluorescence intensity, so that basically that's the amount. The amount of CXCR4 that's on those B1 cells is much more significantly associated with these protective IgMs. No association with the IgGs. So what we discovered in the mouse from cell-specific genetic knockouts, putting them on atherogenic backgrounds, and again, actually it looks to be important in humans as well. So But are these antibodies, we wanted to test then, you know, if these antibodies are associated with coronary disease and unstable coronary disease, again, similar, I told you Sam had the coronary data, the event rate, you know, some coronary calcium studies that he's published, but hadn't before published with IVUS. So these patients, when they come into the cath lab, we not only ask them for 100 mils of blood, we ask them if we can put an IVUS catheter down. So, and we do that, and we predominantly do the same length of segment in the LAD, and you pull it back along a defined speed. We have a volcano, so we're able to get virtual histology, so meaning not only can we say how much plaque is there, but we can say how much is necrotic core, dense calcium, or fibrous. And so the question is, well, what about these results that Sam gave us about the IgM and the IgG? Does it recapitulate what Sam's found in all these other trials? And indeed it does. So you can see for IgM to MDA LDL, significantly associated inversely, because again, remember this is protective, so inversely associated with maximum stenosis, with plaque burden, as well as necrotic core size and the percent of calcification within the plaque. It's positively associated with fibrosis, which is felt to really be a more protective phenotype, if you will, because you lay down collagen and protect from plaque rupture. But nothing associated with the IgGs. So again, consistent with things that Sam had published before. So then we wanted to know, well then what about these plaque characteristics and the amount of CXCR4 that's on the B1 cells of these individuals? And as you can see, there's a significant association with how much CXCR4 you have on your B1 cell and plaque burden, maximum stenosis, necrosis and calcium, again, inverse association, and a positive association with the fibrosis, but no association with lipids. And we looked at other risk factors I don't have up here, like age, diabetes, hypertension. No association between CXCR4 and those things. And this is one of my current RO1s, is to look at more than 50 patients. So we can do a true, really good multivariate analysis looking at covariate. So we're now enrolling 250 patients that we're doing intravascular ultrasound on and doing this deep immunophenotyping. So what we're interested in, and I've been talking to David a bit about this, because we still have several hurdles. So one of which is how would we do this in humans? So we're interested in increasing the amount of CXCR4 on human B1 cells, with the idea we want those cells then to traffic, and I didn't show you the data, but I did yesterday, that when you have more of this, those cells will go to the bone marrow and you'll get higher IgMs, to these protective IgMs, with the idea that it could afford atheroprotection. So in conclusion, the human studies support our murine findings that B1 self-derived IgM to oxidation-specific epitopes like MDA on LDL is atheroprotective. CXCR4 is associated with plasma levels of these protective IgMs and inversely associated with coronary plaque burden, stenosis, and vulnerable characteristics. And that strategies to increase CXCR4 on B1 cells may be an effective way to increase atheroprotective IgM and limit CVD. I didn't show you the data here because again it's mouse, it's flow cytometry and things like that, but I showed yesterday that using a retrovirus to deliver the gene into B1 cells, we can show that we can increase the receptor expression on the B1 cells, and that pops up the serum levels of these protective antibodies in a mouse. So the overall summary about inflammation and immune modulation is that the CANTOS results do support the inflammatory hypothesis in human CVD. HSCRP response to Canakinumab identifies people most likely to accrue the largest benefit. Expense and safety remain concerns in my mind with this drug, and that results support further study and development of immune modulation approaches for CVD prevention, and approaches that could target CVD-specific inflammation pathways may actually allow for greater efficacy with fewer cardiovascular side effects. And we don't have these in our armamentarium now, but I would say they're coming. over the course of the next 5-10 years. I think we'll see, certainly I think we're going to see some IL-1 beta inhibitors hitting market, but hopefully we'll see some more targeted therapies as well. So this is something I pulled off the internet and kind of a hype fancy picture about these results. Drug lowers heart risk by curbing inflammation, and what I cut off here is they're saying a new frontier. So a little bit of, and I cut it off, a little bit of hype, but so I think we have to be a little bit cautious about that, but I think we can be hopeful that it won't be long that we'll have additional weapons for treating that residual risk in our really high risk subjects. So again, my thought is it's an intriguing possibility, but a lot more work needs to be done to make immune modulation for CVD affordable and safe. And I just want to acknowledge the group in my lab, because I showed again much of the cartoon that I showed you were data that we derived from murine discovery, and Aditi Upadhyay is a graduate student in the lab who really did the CXCR4 project. But Sam Morris Rosenfeld, who's an intern here in internal medicine and an MD PhD graduate from the University of Virginia. So maybe someone that you'll want to try to corral over to cardiovascular. He's a great idea and a great guy and an outstanding scientist. So Sam did a lot of the murine, and he did some human translation work that I didn't present here today as well, but with regard to B1 cells. Angela Taylor is the interventional cardiologist that I collaborate with, and which has known her for probably 15 years or more, because she actually is a cardiology fellow trained in my lab. And then she went on to do interventions. So it's a nice collaboration, because we talk each other's language, which helps. And then our collaborators at UCSD, Sam Tamikis and Joe Whitstone. So thank you for your attention. I'd be happy to answer any questions.
That was really exciting.